Hello, my name is Aryan Singh, and I'm here to introduce Ben Ross. This summer, Ben interned under the mentorship of Chris Thompson, working to develop a framework for large language models to generate cyber forensics competitions. Everyone, please join me in welcoming the Ben Ross.
Thank you very much, everyone. So I know that's a mouthful. What I want to talk about first is what a cyber forensics competition is. A lot of us have experience with that through SMCS, but for those of us who don't, I want to discuss what that really entails. Cyber forensics competition is the process of doing a forensics investigation using online artifacts. Forensics is the process of looking at artifacts and figuring out what happened in a specific scenario based on the information that you can find within an artifact. For instance, let's say we're trying to figure out who killed a scientist. We could look at fingerprints left on the scene. We could look at a suspicious alibi. We could look at DNA and clothing fibers and figure out that obviously it was Mr. Lee. But for a cyber forensics competition, it's a little different. What we do is we look at emails that can be sent right after. We look at security camera footage. We look at maybe an online order of a weapon. We look at location coded in the image. The core idea is that we look at we look at online characteristics instead of physical characteristics. Now, on this slide, you actually already saw there was text hidden in that little corner. That's the simplest version of a cyber forensics investigation. Looking for text in slide. Looking for text in some sort of thing hidden in plain sight. But you wouldn't actually see it in this format. You would see it in the format of a flag. A flag looks like this. There's some sort of standardized format within a competition where you look for information that's in this format. This is a flag. As you go through the competition, these serve as a sort of quantitative metric to figure out where students are within the competition. But this isn't the whole idea. To submit to the competition and to be ranked, students also have to construct a write-up giving their explanation of what happened under this mystery. For my research, I simplified cyber forensics competitions to 6 main types of challenges. Disk images, where competitors have to analyze a file system from a computer and figure out what is on it, if there's any important information, how that contributes to the overall storyline. Email files, where they have to look at email threads, figure out if there's any information within emails, or maybe some connotations people were saying within the emails. Network traffic, where 2 or more computers are talking to each other, and competitors get a recording of that conversation and have to figure out information that's within it. Image metadata, which is when you take a picture on your phone, it knows the location, it knows the time it was taken. Sometimes text can be encoded in there, so users can take a look at that. Encrypted PDFs, where there's information hidden within a PDF that you can password open, and database contents, where you have to look at a database and see if there's any important information within it. This simplification allowed us to assess later down the line how effective our framework was for creating these sorts of competitions. Let's go more in depth into a disk image challenge. In a disk image challenge, an image is taken, which is basically a snapshot of a specific part of your computer's file system. This file system has folders within it, these folders have files within them, and one of these files probably has a flag. The contents of the file probably also have to do with the overall story. So this is important to read through for the write-up and then this competition. When you think about going through and solving this sort of challenge, it's different. But what's more difficult is creating it. Not only do you have to test it, so you have to do everything that a student would be playing through, but you have to know how to take a disk image off of a computer. You have to fill it in with mock information. You have to figure out what would be typed in the files that aligns with the overall story. This is a lot of work. For every competition, 1 or more people has to come up with a storyline, create many challenges that match that storyline, test all of those challenges, and then figure out how to deploy those challenges as one cohesive competition for students to play through and learn. This requires significant resources, and it's prohibitive for many groups. It requires money for deployment to host these challenges on computers. It requires time to create these challenges, and it requires a technical expertise to know what sorts of challenges would be well fit for the story. Maybe there's another one, and that's the question that my mentor and I asked this summer. would it be possible to use any sort of technology to make this process significantly quicker? And that's where I introduce LLMs, also known as large language models. I'm sure most of you remember the first time you typed something into ChatGPT and saw your computer talk back to you. For the first time ever, computers could interact in natural language and interact with the world in similar ways how we do. You may be familiar with GPT 5.2, Claude 4.5, Grok, Gemini 3. These are well-known large language models. I'm going to say most of you know GPT 5.2 best. And these can be used to interact with text. But what's actually going on behind the scenes? We think of large language models, most of us, as something that we type in a question to and we get an answer out. But we have to consider what they're a part of. Large language models are a subsection of machine learning. Machine learning is the idea of teaching a computer rules. In traditional programming, I write the rules. For instance, if I wanted to make a chat program, I would have to manually define what would happen no matter what the user says. If the user says hello, the chat program should respond with hi. Imagine using this architecture to create ChatGPT. It would be near impossible, not technically impossible, but near impossible to code for every single possible input that users could give. Humans create the rules in this framework, and that's why we need machine learning. We give many examples of how the model should behave under different conditions. And from that, the computer can learn to predict. But predict is the essential word there. All the first language models did was predict the next token. What did that look like? Maybe I would give once upon a time there was a little to a language model, and I would let it run once. It would produce what would be the most likely next token. Red. Most likely next token. If I plug that whole thing back in. House. Plug that whole thing back in. Plug that whole thing back in. We get that sentence starting to form. Keep in mind that every single time we're running this, we have to feed it everything that's already been said back into the model. But this isn't super useful. ChatGPT is nice for finishing stories. It's nice for creating things that don't already exist. So we need a way to interact in a back and forth structure of the conversation. And so we came up with the idea of users versus assistants in conversation. The user says, "Boil the dog," and then the assistant hasn't responded. A language model will naturally start the assistant response with the most likely answer for what is a dog. A dog is a bird, and it will continue on. But what if we ask something like, "Who are you?" If we ask this to ChatGPT, most of us that have seen this response will say, "I'm ChatGPT, a helpful large language model assistant." But that's not what they're naturally going to do. They're going to take the average answer from all the text that they've been trained on. And when ChatGPT was first created, no one had ever answered, "Who are you?" with, "I'm ChatGPT." So we had to come up with a way to encode that sort of information, and so we created system prompts. This comes before the user prompts and once fed into the model, and it gives it definitional ideas for how to interact with the user. You are a helpful AI assistant. Your name is ChatGPT. You will not help the user create a list of materials. You will not do the user's homework. You will help the user with their homework. Stuff like that. And now the assistant can answer that sort of thing. I am a helpful AI assistant because it knows them. So this is what I wanted to use for my internship. Maybe we could create cyber forensics challenges like this. Give a system prompt that defines you are a cyber forensics challenge generator, and then you should create a challenge where ... maybe a disk image is analyzed. And so the LLM would output some sort of artifact. This has a pretty significant issue. I can't provide people. If I don't like the exact way that the large language model created the challenge, there's nothing I can do with it, which is a problem because we need to tune these competitions. This is a pretty simple fix. We just add a loop back to the user response, and the user can ask something, and the LLM can respond. This is how we are all used to using large language models, how we're all used to using ChatGPT. There's a system prompt that we don't get to see, and then we and the model take turns adding something to the conversation. This is what I tried for a significant portion of the first part of my internship. But there is a more significant issue with this approach. The model cannot test its own output. The model is relying on me to look at what it has created, play through it, and make sure that it fits my standards. This is insufficient. We need some way for the model to look at its own output and understand if it has done what I needed to do. And that is where I introduced the concept of tool call. We still have a system prompt, we still have a user prompt, but we also now have tool definitions. We tell the model, if you say list_files, you will then get a list of files in the folder that you're currently working. This is game changing. The model does not have to give the user the opportunity to respond until it is confident that it has completely finished what it is meant to do, completely finished the challenge that it's trying to create. So let's try this for creating the 6 types of challenges that I defined. We're going to use the modern large language models that we're all used to using. I use Claude 4.5 Sonnet, GPT 5.1 Codex, which is the equivalent of ChatGPT. It's really good at writing code, and Gemini 3 Pro. And the results were astounding. With the old method, I was getting 0% success rates because the model could not iteratively refine what it was creating. This was my success rate with the new model for creating the types of challenges that I wanted to create. GPT 5.1 Codex and Claude 4.5 Sonnet nailed it. First try, without me needing to respond with any user feedback. I didn't need to say, hey, you need to put that in the right directory. Hey, that challenge doesn't actually make any sense. Perfect on the first go. Gemini 3 Pro did quite good, but there was an issue, and it's an issue that I think is relevant to go into. It started to say this. It started to say, okay, I'm sending cold calls, I'll verify execution, I'll verify verification, I'll verify success, I'll verify user satisfaction. Started to get caught in this loop, then started to give itself words of affirmation. Anyway, I'm gonna send people cold. And then it just, sending it down. The reason for this is a little unintuitive. The model, it is natural maybe to say these first few things. And when we think, oh, I'm about to do something, wait, I should probably also do this. I'm about to do something, wait, I should probably also do this. Doing that a few times is natural. But large language models are trained to predict the most likely next token based on what has come before. And if what has come before is 2 lines like that, maybe we do another line like that. Maybe we do another line like that. Most modern large language models have a repetition penalty. So if they start to fall into this sort of trap, they are penalized and are more likely to stop doing it. Obviously, Gemini 3 Pro has not mastered that yet, so I would not recommend using this for the same thing that we're trying to do here. Here's a pass-fail matrix. You can see that every single challenge was passed except for Gemini 3 Pro failing on the image metadata challenge. It wasn't actually related to what the challenge was, it was just kind of getting caught in a loop. And the image metadata is the one with a 67% success rate. All of the other ones were 100%. The time efficiency is something to also consider. Gemini 3 Pro was by far the fastest per success, although it was the only one that didn't have complete success. But this isn't really that important. Each of these challenges would take hours upon hours for a human to create without artificial intelligence assistance. So we're already down to like in 100 of them. 5 minutes versus 2 minutes isn't actually that relevant per challenge. The total cost is something that is relevant, because if this is going to be put in the software that's rolled out to many people, especially if it's meant to help people that already don't have the money or the time to create these sorts of competitions, the cost is something to consider. Gemini 3 Pro is by far the cheapest, but it's important to know that this is something that's in flux. For these models, you pay for every token generated. We can approximate that to a word. Their pricing is changing. I wondered when I saw these results, wow, have models really gotten that much better in the past year? Are we really at the point where they can do all this? So out of curiosity, I was like, okay, how would this have gone if I did this internship a year ago? Pretty well, actually. I expected a straight 0% success rate. These are the 2 new models, Claude 3.5 Sonnet, GPT 4.0. These were the state-of-the-art coding models exactly 1 year ago. And they did decent. Claude 3.5 Sonnet was on par with Gemini 3 Pro, and GPT 4.0 had a 50% success rate. Obviously not great, but with some tuning, it got up to getting being able to make every challenge. This was quite impressive to me, and it shows that what's more important than the underlying model is how you structure it. The architecture of being able to call tools is so much more important. For every single model, I pass in the exact same instructions, the exact same system prompt, and the exact same tool calling abilities. That obviously made far more of a difference than the underlying models did. So you can see modern models compared to the Euro models. It really is quite impressive. Here's the pass-fail matrix when you include the Euro models. The disk image challenge had by far the most issues because, as I already walked through, it requires a lot to create that sort of challenge. You need to know all these different things. But for these models, they often failed on somewhere along the line of creating disk images. The cost efficiency was also studied. I looked at Claude 3.5 Haiku, which is the budget version of the modern model. And it actually was more expensive because it wasn't very smart at knowing I can do this a lot more efficiently which means it ended up using a lot more code to do the same task. So can a full competition be made? If you are in computer team, you know the answer to this because I sent it out to you. I created a full competition using Claude 4.5 Sonnet and sent it out for feedback. How does this compare to a normal cyber forensics competition for those of you who have experience? How easy is this to get into? Can you tell that this was AI generated? What do you think? The pros were pretty good. I had a first draft of this competition in 15 minutes. That is unbelievable when you consider how long these things generally take to create. The storyline was continuous. There was a consistent mystery that you could find clues for as you found flags throughout all evidence. The flags were very well hidden. However, there were some cons. The visual artifacts were subpar. Remember, we're working with large language models. A top large language model researcher once analogized asking a large language model to create a visual artifact, asking a blind man to make you a picture. You can tell him all you want, how you want it to look, but he can't look and see if it actually looks how you want it. That's what asking a large language model to create something visual is similar to. So all the websites, any images look subpar and were pretty obviously AI generated. But more importantly, participants felt like the competition they played was kind of an average of other competitions. That's not horrible. That means it's not a bad competition. But that also means it's not a great one, which makes sense. A large language model predicts the most likely next token. It is by definition an average machine. So we don't give it any reason to go above and beyond. It's going to produce the average version of the challenge that we asked for. So this is why a human needs to stay in the loop. A human needs to have those ideas. It would be really cool if this challenge connected with this challenge. It would be really cool if students could look at this folder and find a password that they need to use 5 challenges later on. They need to write it down and remember it because it will be important. That sort of human input is what's critical for these sorts of challenges. That's why I'm not suggesting completely replacing the workflow using a large language model generating these competitions. This is definitely viable overall. In the future, I'm looking to automate deployment because the model produced these challenges, but they were just sitting on my computer. To get them to the point that my computer team and anyone else could play them, I needed to do all the deployment manually, put them on someone else's computer, get them a website address, pass out that website address. That took a lot of work on my part. The sorts of people that don't have the time to be creating these competitions probably also don't have the time to deploy them. I'm also looking to package this into a visual software. Most of us are used to using computers by clicking around in Windows. I needed to type in everything onto my command line, which is basically what I'm telling the computer exactly what to do. For this to become more accessible, I would like to create a way for users to use this as a visual software instead of typing in. I'd also like to test more models. I was constrained by the amount of dollars in my wallet because each of these outputs costs some amount of money. But I would like to see what really is the best model. Although we have seen that most model models are more than capable of doing what we need to do. I would like to acknowledge my SMCS teachers. This has been the best 3 years of my life in this program. I am so happy here, and I'm so grateful for everything you all do to make it incredible. Mr. Ketterpole, Mr. Gerard, Mr. Easton, Mr. Lee, Mr. Kingman, all of you, I'm so grateful. I would like to especially thank Mr. Easton for involving telling us to participate in the cyber forensics competition in 10th grade. Had he not done that, I may have never discovered how much I enjoyed this weekend. I would like to thank the junior committee. This event was almost entirely organized by them. It takes a lot of work, I know, and I am so grateful, and so is every other senior, even if they don't realize how much he's gotten. I would like to thank Chris Thompson for his incredible mentorship. Our calls together just felt like talking to a friend. He is so smart, he is so knowledgeable as to his field, and I love learning from him. Lastly, I would like to thank all of you for listening. Thank you. Yes, indeed. So image generation AI, I mentioned images being subpar. That wasn't as much of an issue. The bigger issue was the website. The websites were good. If you have used agentic coding tools, you will learn to recognize a flawed coded website, or any website that has been coded by AI, because it falls back on the same tropes. Buttons don't really align, colors are kind of neon and look ugly. That sort of thing is what we really don't have a good solution to. I'm hopeful that more AI advances will get us to the point where websites will be carried by large language models. But at this point, I'm not exploring it because it's not really sensitive. Yes, Alex?
Sound like automated.
The text? I thought the text checked out. Cyber forensics competitions, the text, like the exchanges between two people over email, are generally pretty corny, like, oh, meet me after class, I need to figure something out. Like, okay, AI can mimic that pretty well. You expect, some sort of corny dialogue to be in this room. And so I didn't notice a significant difference with how AI constructed that dialogue versus how that dialogue is being constructed.
Yes, Shia? Did you want your biggest takeaway was from it? Like the
It is so powerful. I mean, if you give a one sentence prompt to a woman, you are going to get a response that is proportional to the amount of effort you put into that question. If you give it as much context as possible, tell it everything about what you want it to do, about what it's looking for, about what mistakes it made that it has that you don't want it to, it becomes so much more effective. It's true for using ChatGPT online, and it's true for using a lot of programs. That was my biggest thing. Yes, Ned?
So throughout your internship, were there any moments where you felt like giving up? And if so, how did you muster the courage to keep going?
Thank you for that thought. Yes, but for the first month or so, I really was focused on trying to get the conversation to work. The model outputs one shot a working artifact for the challenge. This did not work because it simply could not understand. I was getting discouraged. I was getting caught up in the need to figure out, well, maybe I'm not prompting it well. That was the issue. The issue was